Hey everyone, and welcome back to AI.Code.Cast. Today we're doing a deep dive on a pretty cool problem. It's called longest substring with at least k repeating characters.
Yeah, it pops up in a lot of different areas like bioinformatics and text analysis, anywhere where finding those repeating patterns is really important.
Okay, so before we get too far, uh, can you just remind us what the problem actually is?
Sure. So basically, we're given a string. You can think of it as a sentence or even something like a DNA sequence. And we also have this number K.
Oh, right. Yeah,
Yeah, exactly. So the goal is to find the longest part of that string, the substring, where every single character appears at least K times.
gotcha. So like if our string was abcapsive and k was 2.
Then the longest substring would be looking for would be abgex because each character in that part shows up at least twice, right?
Right, makes
Mm.
sense. So where should we start with this one?
Well, we could always try the brute force method just to get a feel for the problem.
Okay, brute force.
Yeah.
But I have a feeling that might not be the most efficient way to go about it.
You're absolutely right. Brute force can be really slow, especially when you're dealing with longer strings.
So why is that? Why does brute force struggle so much with this particular problem?
Think about it this way. With brute force, you'd have to check every single possible substring within our string.
Oh, wow. So it's like trying every single combination on a lock.
Exactly. And the longer the string, the more combinations you have to try, and it just becomes way too time consuming.
I see. So brute force is out of the question for large data sets. What's a more clever approach?
Hmm. Well, what if we try to break down the problem into smaller chunks?
Break it down. How would we do that?
Well, we could focus on identifying and eliminating the parts of the string that are definitely not part of the solution.
Okay. So we're talking about finding those dead ends that can't possibly contain the longest valid substring.
Exactly. And the key is to use those invalid characters as dividing points to split the string.
Invalid characters, you mean the characters that don't appear at least k times?
Yeah, exactly.
Yeah.
We can use those as boundaries to split our original string into smaller substrings.
That's really clever. So we're essentially getting rid of sections that can't possibly contain the solution.
Right. And then we can recursively apply the same logic to those smaller substrings.
So we keep dividing and conquering until we have substrings where all the characters meet our k requirement.
Exactly. Then we simply pick the longest substring among those.
This divide and conquer approach sounds much more efficient than brute force.
It is in many cases,
Oh.
but it does have its limitations.
Oh, really? What kind of limitations?
Well, for one thing, recursion can be a bit memory hungry, especially when you're dealing with very long strings.
Right. So while divide and conquer is faster than brute force, it might not be ideal if memory usage is a concern.
You got it. So it seems like we need a method that's both time efficient and space efficient.
Okay, so we've ruled out brute force and divide and conquer. What other tricks do we have up our sleeve?
Well, there's this really elegant technique called the sliding window approach. It's designed for efficiency, both in terms of time and space.
Sliding window. I like the sound of that.
Yeah.
Tell me more.
Imagine a spotlight moving across our string. That spotlight is our window, and it highlights a substring at any given moment.
So instead of generating every single substring, we're just cleverly scanning through the string.
Exactly. And we control the spotlight using two pointers that define the beginning and the end of the window.
I see. So it's like we're only focusing on a small portion of the string at a time.
Precisely. And the magic lies in how we expand and contract this window based on our K repetition rule.
Expand and contract. So we're dynamically adjusting the spotlight as we go.
Exactly. We'll dive into the mechanics of this expansion and contraction in more detail later, but it's this dynamic nature of the sliding window that makes it so efficient.
This is sounding really promising.
Mm.
We're scanning through the string, adjusting our window as needed, and somehow that's going to help us find the longest valid substring.
It is. We're going to break it down step by step so you can see exactly how it works. All right, so let's dive a little deeper into this sliding window approach.
Yeah, I'm really curious to see how this spotlight actually moves across the string.
Okay, so picture this. We have these two pointers. You can think of them as the edges of our spotlight. We'll call them window start and window end.
Okay, window start and window end.
Got it. And they both start at the beginning of the string.
So our spotlight is initially just shining on the first character.
Exactly. Now here's where the movement comes in. We're going to
Yeah.
expand the window to the right by moving the window end pointer.
So we're basically widening our spotlight.
Right. And as we expand, we're keeping track of how many times each character appears within our window.
So it's like a running tally of the characters as our spotlight moves along.
Exactly. And this is the key part. We only expand the window as long as every single character inside meets our K repetition rule.
Yeah. So if we hit a character that hasn't appeared at least k times, That's when we have to adjust our spotlight.
You got it. That's our signal to shrink the window from the left. We do that by moving the window start pointer to the right.
So we're kind of trimming the spotlight from the left side.
Exactly. And as we shrink, we also update our character counts accordingly. We remove the character that window start is pointing to from our tally.
Okay, so this process of expanding and contracting continues as we scan through the entire string.
Right. And the whole time, we're keeping track of the length of the longest valid substring we found so far.
So even if we shrink the window and miss a valid substring, we still have a record of the best one we've seen.
Exactly. We
Yeah.
never lose sight of the best solution. Oh, and there's another cool thing here. We don't actually have to recalculate all the character counts every time the window moves.
Wait, really? That sounds like a lot of unnecessary work.
It is. And that's where the efficiency comes in. We only need to update the count for the character that's either entering the window as we expand or leaving the window as we contract.
I see. So each step is actually quite simple.
Yeah, it's all about those small incremental updates.
So the sliding window is expanding to find new possibilities and contracting to ensure validity, and all the while it's keeping track of the best solution it's encountered. It's pretty amazing how it all works together.
It is. It's a really elegant way to approach this problem.
Okay, so I think I'm starting to get the hang of this, but it'd be great to see a concrete example. Can we try it out with our string abcab and a k-value of 2?
Arse. Let's walk through it step by step.
All right, so we've got our string abcab and our k-value is 2. Let's see this sliding window in action.
Okay, so remember our pointers. Window start and window end.
Yep. They both start at the beginning, right?
Exactly, at index 0. So our spotlight starts off shining on just the first character, the A.
Okay, so we've got just one A so far.
Right. We need at least 2 AS to make it valid.
So what do we do?
We expand the window, we move window end, one step to the right,
Okay, so now our window covers Abe.
right? 1A and 1B.
Still not enough repetitions. Let's keep expanding.
Okay, moving window end again. Our window now includes ABC.
So we've got 1A, 1B, and 1C. Still waiting for that repetition threshold of 2.
I know, right? Let's see what happens when we expand again.
All right, hitting that window end button.
And now our window shows AB-K.
Ooh, 2AS.
Exactly. But we still only have 1B and 1C.
Right, we need all the characters to appear at least twice. Keep going.
Moving window end again. Our window now covers ABCAB.
2 A's and 2 B's, but still only 1 C. Getting closer, though.
I know, it's exciting, isn't it? All right, let's try expanding one more time.
All right, spotlight, get bigger.
And there we have it. Our window is now ABCAB-y.
Finally, every character appears at least twice.
Exactly. So this substring ABCAB-y is 6 characters long. It's a strong contender for our longest valid substring.
But we're not done yet. Right?
No, we need to keep exploring to see if there's an even longer substring hiding in here.
So we keep moving window end to the right.
Exactly. Let's see what happens.
All right, expanding the window again.
Now we've got ABCAB-y, still looking good.
7 characters. This sliding window is on a roll.
It is. But watch closely as we expand to include that final B.
Okay, so now our window covers the entire string abcab B.
Right. We still have enough of each character, but this is where our optimization kicks in.
The optimization you mentioned earlier about not recalculating all the counts every time.
Exactly, because even though this expanded window is valid, we might be able to find another valid substring that's just as long or even longer by shrinking the window from the left.
So we should try moving window start.
You got it. By shrinking the window, we might be able to find another valid substring that starts later in the string.
I see. So it's not just about finding the first valid substring, it's about finding the best one. And that might involve some strategic shrinking along the way.
Exactly. And in this case, as we shrink the window and try different starting points, we'll discover that ABCAP-Win, the substring we found earlier, is indeed the longest valid substring.
Wow, what an amazing journey. We started with this seemingly complex problem, and we've explored multiple approaches to solve it. Brute force, divide and conquer, and finally, this elegant sliding window technique.
And along the way, we've learned about time complexity, space complexity, and the power of dynamic algorithms.
This deep dive has given me a whole new appreciation for the beauty and efficiency of algorithms. Thanks for guiding us through it.
My pleasure. And to everyone listening, I encourage you to try implementing these algorithms yourself. Experiment with different strings and innate values, and see how the sliding window dances its way to the most efficient solution. Until next time, on AI.Code.Cast, happy coding!